Hi, hi. My name is Andrew Gunawan, and this is my student ID Z5461893. And today, I will be presenting my final experiment. This presentation will explore Kepler's law of planetary motion, their significance in celestial mechanics, and the insights gained through practical simulation. Let's dive in how these laws are explaining the harmony of planetary motion and their role in understanding of our universe. Okay, what are the Kepler laws? Kepler laws describe the motion of planets around the sun. First, law of ellipse, which planet move in elliptical orbit with the sun at one of the two foci. 2. Law of equal areas. A line in connecting a planet to the sun sweeps out equal area in equal time intervals, meaning the planets have moved faster when closer to the sun and slower when further away. Law of harmonies, the last one, is gonna be the square of a planet's orbital period is directly proportional to the cube of average distance from the sun. This highlights the relationship between the planet orbit size and its orbital period. Okay, next is the answer question 9a. Is the planet and moon's orbit a shared center of a mass called the barycenter? For a planet-moon system, the barycenter is closer to the planet due to the larger mass. For question B is in the Earth-Sun system, the barycenter lies within the sun because its mass is overwhelmingly larger. When the sun's mass is reduced or the planet mass increases, the barycenter shifts slightly but remains within the sun. C. Comparing the system, the location of barycenter in a planet-moon system, it is within the planet, but for a sun-planet system, it's inside the sun. Last one is gonna be the relative motion. In a planet-moon system, both bodies exhibit noticeable motion around the barycenter. However, in the sun's planet system, the sun's motion is negligible due to its large masses. Okay, this is the question for 11. So, from the simulation, when the grid lines are turned on, the distance between each grid line represents one astronomical unit, or we can say 1 AU. Next is going to be the 0.5 AU. And here the result from 0.5 to 2 AU. We start with 0.5 AU, 1.0 AU, 1.5 AU, and 2.0 AU. Okay, and here's the table of distance AU and the orbital period days. Okay, so coming to question 14a, we aim to verify the Kepler's third law, which states that the square of the orbital period t square is proportional to the cube of the semi-major axis or distance r3, with the ratio remaining the constant across all distances. To test this, we calculate the T2 for each orbital period. The computed R cube for each distance and divided by T square by R cube to check if the ratio was consistent. While the results confirm the proportionality between T square and R cube, the T2 over R3 ratio was not constant. This suggests that the discrepancies were likely due to the surrounding errors or inaccuracy in the simulation data, rather than a violation of the Kepler's third law. Despite these minor inconsistencies, this relationship between orbital period and distance was still evident, validating the core principle of the law. Question 15a is gonna be Mercury has the fastest orbital velocity because it's closest to the sun. And the question B is the Neptune has the slowest orbital velocity because it has the farthest from the sun, experiencing a weaker gravitational pull. The part C is the difference in orbital velocity are explained by the gravitational forces, such as decrease with the square of the distance, and the Kepler's third law, as distance increases, the orbital period increases and the velocity decreases. Lastly, is the question 16 is the orbital velocity is determined by the distance from the central mass, like the sun. Kepler's third law demonstrates the harmony between the orbital period and distance. This simulation highlights the roles of gravity and velocity in maintaining the stable orbits, emphasizing the balance required for circular or elliptical path. And here are the references, and yeah, thank you.